energy behavior. So, yes, modeling and forecasting of energy behavior at across various scales. I think yeah. So I'll start off with sort of a very brief overview over typical modeling methods for forecasting energy in buildings, and we can sort of categorize them into three main categories. That is physics-based models that are generally derived from governing laws and are typically fully interpretable, which means we can understand the mechanics. We can view the mechanics of the physics as such. Then there is data-driven approaches, which are, I guess, the trendier approach to forecasting energy in buildings, also known as black box models. So these typically we can see the structure and parameters derived from data. So there is no need for domain knowledge using the data-driven approaches. And then there are hybrid models that take a bit of both. So they contribute to both physics-based and data-driven approaches, where you supply the structure from physics, but the parameters are learned directly from data. So obviously the focus here is on data-driven approaches, given that they are becoming extremely popular across fields and not only across fields, but also in energy and forecasting of energy or time series forecasting. So they're popular because they're easy to implement. If you have enough data, you can got data. So they're good at extracting spatial and temporal structures from data without requiring mechanistic understanding of the phenomena. But the issue is that they tend to be not interpretable, which means they don't hold any physical correspondence with the governing laws with the laws of physics and principles of physics that govern the observable behavior in buildings. They can be quite data intensive, and for them to even work well and generalize well, you do not necessarily have a lot of data, but you need to have representativeness in the data. Lastly, they also have trouble generalizing for out of sample scenarios. So the broader goal of this work is to work towards improving the generalizability, so the ability to generalize for out of sample scenarios, to improve data dependency and even the interpretability of such models by shifting from the typical approach of fitting models to data towards the idea of incorporating physics in the machine learning strategy, so combining physics and data. And the result would be models that will generalize better. They are more data efficient because you're not starting from scratch, but you're supplying principles that we already know and have known for a while, and also are of course interpretable because the structure of the governing equations are being maintained. So this is a developing field, and there's a lot going on in this field. But the focus of this work today is a subset of what I've just said, and I'll be focusing on the generalizability aspect. So how can we improve the ability for these energy models to generalize across, they also offer out of sample scenarios, but also across similar energy systems. And the idea here is to leverage the governing structure that is innate in physics-based models. So just to kind of give a last comment on this, the idea here is that we have a model for, let's say, a room in a building or a zone in a building, and we want to explore the ability to reuse and adapt that model in similar systems that are undergoing similar phenomena. So why should we start from scratch and building fresh models for new data, where we can actually adapt physics-based models from previous or related systems? So one way of doing so is by supplying. So I apologize for the display. It seems that it actually is the screen. There's need to be some brackets there. So I'll start off by sort of explaining how we can structure the physics for incorporation into the machine learning framework. And here I'm showing an example of a thermal zone, a very simple thermal zone, which is sort of governed by different sources of energy. And we can represent this into a low-rank resistance capacitance model, or known as RC thermal networks, where as such you represent in a very standardized way the energy fluxes inside of practically any system. So for this very simple case, we've got on the right-hand side, we can see that we're representing, the influence of the external temperature, of HVAC, of temperature coming from an adjacent room. And in these networks, they're composed of resistors and capacitors. So the resistors represent thermal resistance, and the capacitance represents thermal storage. So we can sort of already standardize across systems energy exchange in a standardized format. But let's focus on to make this even simpler, and focus on a simple example of a wall. So the energy exchange through a wall. So we have three resistors. The external the convective, so the one on the left hand side represents the convective transfer from the external temperature to the facade of the wall, and then the actual conduction through the wall, and then on the right hand side the convection so the resistor on the right hand side represents the convection, the exchange between the surface of the wall on the inside and the internal side of the room. Now, this is just a simple one-dimensional example which I will carry through to the work. So we can further standardize and represent this system in a more standardized approach using state space models, where as such we can define for every node. Actually, I went ahead of myself. I'm sorry there. So each node, the dynamics of each node, we essentially are differential equations, and we can specify these by informing them from the governing heat balance equations that are very well known. So as such, we're looking at a differential equation for each node, which we can then represent we can inform the parameters directly from physics. So the parameters in this case can be drawn from data, but in this case, because I want to carry forward interpretability, and we all have this very well-known understanding of energy transfer, so we can inform the R and C parameters of those differential equations directly from basic convection, conduction, and storage equations. Now, we can then further represent these differential equations as a standardized state-space model. So the goal here is that if we want to transfer and we want to sort of adapt models, physics-based models from one system to another, we need to have a standardized representation of these systems. And this state-space models gives us such a standardized representation. Now, state-space models, which specifically here, discrete time, linear time invariant state-space models are composed of two equations. One is the state equation and one is the output equation. The state equation describes the relationship between the states. So in this case, the states we are informing. So the states we are informing as the temperature on either side of the wall, and the output of interest here is the internal node, because it is the one that is most critical post conduction. So it is the one that is influenced and that captures the dynamics given the external temperature conditions. So what I want to focus on though here is that in the first equation, the A matrix, so this matrix on the first equation here, is actually the most important part of this system, because it explains and describes the governing dynamics of the conduction itself. So this is basically the matrix of coefficients, and by multiplying it to the state vector, it updates the states to the next time step, and this therefore contains the juicy information that describes the governing dynamics. So in general, just to give a quick overview, when we want to translate an RC network to a state-space model, it's for thermal systems, it's very convenient to, again, use the nodes as the states. So the nodes become the state vectors, and what I did not mention is the B and the U component. So the U is an input. So it's an external noise or external forcing onto the conduction. So in this case would be the external temperature, which is we can think of as a control variable in the energy transfer to a wall. So the A, I repeat, is taking care of the conduction through the wall, and the B is describing the relationship, the effect, the influence of the external temperature, which is a control signal, onto the conduction dynamics. Now, if I go a step ahead, if we then substitute these states into the state space equation, we can then derive the A, B, and C and D matrix either from data, as I've said earlier, but also we can derive them from directly from physics, because we have these field balance equations as such. We just use the differential equations we derived for each node and the RC network to inform and populate these matrices. So, okay, so that's kind of like slightly the boring stuff, but this is for loops is the most interesting. So when you have a state-space model and we describe it directly from physics as such, we're building a model in continuous time, right? Because the differential equations are existing in continuous time. Now to solve the model, which means to run a simulation using the model, we have to discretize to discrete time. And to do so, we take the matrix exponential of the matrix that gives us a solution of the system, resulting in a time series. So in this case, I'm plotting here the temperature for the two states, for the internal surface of the wall, the external surface of the wall, and I'm plotting them as a function of time, which is how we are used to seeing time series as a function of time. But by the way, in the solution, I'm solving for a given time step. So when you go from continuous time to discrete time, in this case, I'm looking at hourly time steps. So I've set dt to 3,600 seconds. Now, if you plot if you were to view the states against each other, so if you were to plot them against each other, then, or if you plot all states against each other, in this case, I'm looking at only a two-dimensional problem for visual purposes, then we look at what we call the state space. And as such, what we see is a trajectory in time of the full state of the system. So any point in that space describes the full state of the system at a certain moment in time. Now, if I were to go a step further, the point of interest is here is that even from the structure of the linear time invariant state space model, we can see that any observed time series, any dynamic system we observe in life, whether it is simulation or whether it is data, we can decouple that. I mean, hypothetically and theoretically, but my point is that any dynamic system is composed of the actual dynamics, and which look very smooth in the state space, and the noise and signals. Which is what makes the trajectory so squiggly when imposed onto that smooth trajectory. So on the left-hand side, we're looking at a simulation only using the A matrix that describes the trajectory towards thermal equilibrium at any energy condition. In this particular case, I'm using the energy condition I use for the first plot. And on the right-hand side is the weather signal that is what is influencing what is sort of disturbing, let's say, the smooth trajectory. And the focus of, again, my work here is because is on the dynamics. So if we want to capture governing behavior and we want to model the governing behavior to improve the generalizability of these models, then the goal here is to leverage not the higher order, the observed time series, but we want to dig in and utilize the structure of the dynamics of the problem of the governing physics model. So by that I mean we look at the state space decoupled in a decoupled way. So just to give you an explanation of what this is, I'm sure some of you know this probably. So in thermal sense, the state space here, this particular trajectory describes the temporal evolution of the temperature states. So because that node represents all states of the system towards an equilibrium point. And in this particular case, I'm choosing one trajectory. So if I were to visualize this as a wall, on the left-hand side, I've got the outside air, on the right-hand side, I've got the inside air. And so let's say we're going from outside to inside. So the convection itself would take this trajectory. And if you notice, so at first, the outside drops quicker, of course, than the inside because of conduction, and that would result in that shape of trajectory. And then, of course, suddenly, towards the end, towards steady state conditions, that even the sort of the behavior of the way the inside temperature drops rapidly is reflected in the geometry of the trajectory. Now, this trajectory is governed by an underlying field, a vector field. And that vector field is governed by the eigenvectors and eigenvalues of the A matrix. So if you know the eigenvectors, again, this is all linear. So this is, of course, for this particular scenario, this is all it holds because this is all linear. So, and it is being represented in a linear fashion. So yeah, so this trajectory, sorry, this vector field is governed by the eigenvectors of A of the A matrix, which is what I said, which is why earlier I said that that is really important, that A is sort of the kernel of these systems. So if we were to start from different initial conditions around the vector field, we would reveal the geometry of the structure of the governing dynamics, basically in this case, the geometry that is governing conduction through the wall. So again, away without the influence of the external temperature and other noise, so-called noise. These are also called, by the way, phase portraits of phase, and actually some of them can be really beautiful. I come from an architecture background, and I've always been really fascinated by the geometries that even real systems and chaotic systems can produce. So the point here now is that, so if we look at, let's say, a thicker wall, a variable parameter, it's essentially a different system. Obviously, the geometry and the structure is going to change. But what fascinates me is that they are the same language. So if they're the same, you can obviously see obvious similarities, and this kind of like begs for asking certain questions, which I will ask in the next slide, not this one. So if we were to look at multiple thicknesses, here I'm plotting multiple, I'll go back one more. So the rate of, this is the rate to reach the steady point is also informed by the thickness of the wall. So the thicker walls obviously take much longer efforts to reach the thermal equilibrium. So the blue ones are the thinner walls, and the purple or wine color is a thicker wall. So again, we can also reveal, if we are able to actually extract eigenvectors and eigenvalues from data, and there are methods such as POD or dynamic mode decomposition that give you these dominating sort of modes, we're actually able to reveal these structures even of real systems. So the one on the right-hand side are actually equivalent versions of the same problem on the left-hand side. This is for the top, of course. So on the top we have the structure I've just shown you, and on the right-hand side I'm showing a finite element simulation of the same problem. So this is in place of, let's say, real sensor data. And once I had the data, I decomposed that and extracted the eigenvalues. And as you can see, you can, in a very fundamental sense, in a very fundamental space, you can compare the difference between physics and what is actually real. And this, I'm doing the same also for across systems. So the bottom side is for a 0.2 meter thick wall derived by physics, and on the right-hand side is a finite element simulation derived for a thicker wall. And you can still see, of course, similarities. So this begs the question whether we can actually transform these geometries and transform across these subspaces as a form of generalizing these models and leveraging from physics to data. So leveraging the governing structure of physics to data. So this is a big promise I'm making. I'll sort of kill the story now, is that at the end of I'm going to show us an approach that goes towards this. So this is quite a big challenge. And so, as I said, this begs the question, so can we leverage these system invariant representations of energy systems to improve forecasting generalization for out-of-sample scenarios, but also across related systems? So the thing is here is that typically, when we want to in typical data-driven modeling, this we would try to do with like sort of calibration methods. But the thing is, this is not a minimizing bias approach. There's no bias to minimize. This is not bias minimization, but rather this is a task for domain adaptation, also known under the umbrella of transfer learning. So domain adaptation is a growing field, but mostly in the visual and image-based areas. So from literature, domain adaptation is used to transfer, let's say in this particular scenario, they want to calibrate, they are lacking labels, let's say, for certain actions in some target view, but they have only the labels in the source view or from a different camera angle. So they try to train this transformation to translate the labels, train the transformation, and then transfer the labels from one camera to predict also from a different camera, because the phenomena, the subject is the same. So if we're able to capture this transformation, which in a sense represents the change of camera view, then we can efficiently also predict the labels for the that are missing in the target view. So how is this done? It's done using a method called subspace alignment. So the source and target data are projected onto subspaces that are essentially the eigenvectors. In this particular case, I used PCA, which is a principal component analysis, a method of decomposing a set of data into its component features that explain the most variance in the data. In this particular case, these features have no physical meaning, but in physics, and as we've seen earlier, they do. So once you have these eigenvectors, the data is projected onto this, and then a transformation is sought between the source and target eigenvectors, and the transformation is then used to project the labels and predict the labels in the target view. Now, in their case, in the typical case of domain adaptation, the source and target are both data, and in my case, in our case, the idea here is to actually leverage physics as the source. So we have the eigenvectors that's not coming from data, it's coming from knowledge about governing principles, which we know quite well. So the goal is to extract the eigenvectors from data and learn this transformation. So in a more illustrative way, we have the state-based model on the left. We have we've got the data on the right, which, let's say, if this was not a simulation, so for this case study, I generated data from a simulation model, but this could easily be data from sensors, let's say, on either side of the wall. And so we've got the linear state-space model. We can extract the eigenvectors because we know them directly from physics, as I said. So that's your subspace. The same in the case of the target, we can infer the subspace by decomposing the data into eigenvectors. Here I'm using principal orthogonal decomposition, but you can also I've also explored methods such as dynamic model composition, which I won't talk about too much today. So they both give you orthogonal vectors, except that DMD gives you non-orthogonal vectors, and that's I've done some experimentation with it, but I think it's best not to talk about it today. So then the goal is, of course, to seek for a linear transformation between the two, because again, these linear independent vectors are in linear space, which means that what we need is a linear transformation between these vectors. So I do this using a shape analysis method quite a classic method called perplexity analysis, which has been used slightly in this approach, but is known for other things, for aligning geometries. So when we have these subspaces, we project so we use the state-space model to project data that is cheap to generate, right, onto the subspace. We have the available data, a limited available data on the measurement side, and the goal is to align the two and then forecast beyond what's available in the blue stuff, so the target data. And so just a quick overview over the manifold alignment methods. So we start off with the source data and the target data. We project onto their separate subspaces. That gives us kind of a squashed representation. Actually, it brings them closer together, which is why it's done. So it makes the alignment more efficient and more effective. And then we perform a singular value decomposition on those projections, which then gives us a rotation matrix, a scaling matrix. And with these, we're able to then apply to any source new data generated from the source, from the state-space model, and then hopefully we would apply the transformation. It will result into a forecasted data. So one thing I mentioned here is also at the end, because what we're doing is when we do the transformation, we lift back into the space, and this causes some trouble, which I'll be happy to discuss today. But I'll also show a slide on that later on. So I'll show two scenarios where this could be used. I hope I'm okay for time because I'm not stopping this time. Okay, so I show two scenarios how this could be used. So the first scenario is interesting. Okay, so the first scenario is what I'm going to call calibration, where let's say we have a physics-based model of a 0.2 meter wall, And we have a simulation model. By simulation, I mean a numerical model in a software called Energy Plus, which is widely used by the energy community to run sort of numerical simulations, and which here again is in place of real sensor data. So we have a physics-based approximation of the system, of a real system, and we have data from the real system. And the goal, of course, is to leverage the former to forecast ahead of the latter. And for example, and I'll go to the next one. And the second case I'll show is again now is cross system generalization. So the idea of adapting some model that we have, some physics-based model that we have from some system. It could be, for example, we have a calibrated physics-based model that we spend a lot of time doing for a particular zone in a building, and then we want to adapt that to a similar zone undergoing similar circumstances. So how do we use this approach to kind of like transform across different systems? So I start with the first one, and so the state-based model, the physics-based model, was already quite accurately capturing the simulation data, the numerical simulation data. But even though the discrepancy was there, this approach still able to calibrate further. So if I zoom in, it's terrible resolution, I apologize, but you can see that the red, so the solid black line is the dotted line is the source, which is coming from the physics. The solid black line is the data that we have from the actual real system, and the red line is what is transformed from the source to the target. So it fits quite nicely on the target. This is always the case. So if I go to the second example, which I think is for me which was more of the main goal. So we have, let's say, here we have physics-based model describing a 0.6 meter wall, and we have the target here is data coming from a 0.2 meter wall. Again, this is numerical data, and so the dotted line is the 0.6 meter wall, which is the physics. And the squiggly one, the noisy one, is the thinner wall, which is from the data. And as you can see, the transformation was nicely learned. And also, it was mentioned the other plot is that we're actually forecasting too. So we're only training on this part, and then we're forecasting 1,000 hours ahead. So the transformation is then used on the new data generated. So it's generated onto the transformation is learned on this, and then it's applied to this to give us the alignment as can be seen here. And you can see how the area of course changes. So the red line on the bottom is going to show the difference in alignment, the difference post alignment. So here I also repeat this now, rather than changing thicknesses only, we're also changing materials. And because they exhibit similar behavior, we're able to repeat the same alignment. So as you can see, the dotted line on the right hand side fits quite nicely from what was physics-based system for a different wall. Now, again, this doesn't always work. For certain cases, such as in this one, for example, we get we can see that it has trouble dealing with certain noise. So the alignment isn't when it goes from a noisy signal to a smoother signal, the pitch exhibits some issues. And to investigate further, we can look at what's happening in the embedded space. So the on the left hand side is this is what happens when you project the source and target data onto the individual subspaces. So you can see this is the top time series is a projection into the embedded space coming from the physics-based model, and the noisy signal is the projected from target, and the transformation happens quite well. So the red line, it fits quite nicely to the actual, but when lifting it back up to the real space, it loses that alignment, and this is an issue that needs to be resolved. And there are various ways to do this. One of them could be to learn a better decomposition of the eigenvectors, because this is why it's being lost. In fact, when using dynamic mode decomposition, which more accurately captures these modes, because they're closer towards the real physical modes, this alignment was better. But because it's non-orthogonal, gives us an non-orthogonal subspace, it doesn't work for situations. So before I can just present it, I have to put this further. So the broader goal, if we're given the context of this issue that I've just explained, if we go back to the broader goal, so we're looking at also data dependency and interpretability. And one of the next steps we would like to explore is to recover the continuous state-space geometry underlying measurement data. So the goal is, rather than doing alignment on the predicted data and subspaces, rather, since we have the access to the geometry, is perform the alignment on the actual state-space geometry itself, which would then bypass these issues of lifting and projecting. So there's one thing I'd like to point out. What you're seeing here on the left-hand side is what you've already seen, which is a sort of physics-derived state-space model. But on the right-hand side is a data-derived state-space geometry. But you can see that it's not as smooth for the same problem, but it's not as smooth as the physics space. It's because it's the discrete time. So you get the jumpiness because it is coming from a discrete time data, and typically the data we deal with in everyday life and that we get in buildings, that we measure them, is always going to be at time steps. You're obviously never going to have continuous data because it's physically impossible. So, this basically tells us we cannot recover the dynamics only from data. So we need to leverage the physics that is smooth because it's coming from continuous space, even though it's discrete. This one on the left, it's still coming from continuous space. So how can we leverage this smooth geometry to recover the smooth geometry in the target space? So that is in the basically what is underlying the data. And this is obviously a very difficult problem, but I have hope because we can treat these systems and represent these systems geometrically in this way. There are some ways where we can actually find transformations to nudge the discrete time geometry closer towards the smooth trajectories that might uncover, close towards the continuous time dynamics of the actual data. Now, if I were to, this is explaining pretty much the same thing, and if I were to also show, so if you were to increase the time step, of course, of the discrete time system, you'd get a much smoother trajectory, but we don't always have that resolution of data. So generally, when we measure buildings, when we measure environmental aspects of buildings, or for any dynamic system, it's not always possible to get that resolution of data. So what do we do when we have sort of high resolution data? How can we uncover this governing dynamics? By the way, the point of all this still is to incorporate the governing dynamics for better forecasting models that remain interpretable, that improve generalizability, because if you recover the governing system, with geometry, then essentially you can have any initial condition, and you're able to forecast for any scenario, start with any initial condition. So I won't say too much about that, but the second aspect that we'd like to go towards is discovering related state spaces. So along with the idea of cross-system generalization, but by thinking of systems as a population of systems along manifolds. So the idea is that, again, because they're related, and when we think of dynamic systems in this sort of viewpoint in this vector space point, then we can start to think about how they are interrelated along differential geometry. And one way of doing so is using manifolds and manifold learning to learn not only just the location of the individual systems but also you can interpolate between systems and uncover other systems. And there are various interpolation methods, like obviously linear interpolation, geodesic, Euclidean, and so on. But one little very simple attempt from my end is to go again from a source system that is physics derived and the target system which is coming from the data, so as we've just witnessed for the same wall problem. And what I've done here is that I've tried to interpolate between the two systems. So how can we have these views of we have these views of, the physics-based state-based and the data-based state-based, then why can't we nudge the data-based state-based closer towards the physics, such that, or actually sort of the other way around, such that we can, retain certain properties of this A matrix, of the smoothness of and symmetry of that A matrix that contribute to the smoothness of, continuous time trajectories, and so, but towards what is happening in the real data. And this very simple, but attempt here, not so successful, is just simply showing, you can see very closely the dotted line. So the first one is that interpolation equals 0, where both systems are source and target at their own positions. So the red is the source, the black is the target. On the left-hand side, we're seeing the time series as a function of time. On the right-hand side, we're seeing it as a state space, decoupled, of course, from the noise. Now, the bottom is interpolation 0.5, so you can see that there's a system in between them, which is the dotted line. What this means, I don't know. What it relates to, which material properties or what physical aspects it relates to, I don't know. But that's part of the research question. And how do we parametricize this interpolation such that it actually carries forward meaningful correspondence? And again, this is t equals 0.8, so you can see that it equals the target here, even on the right-hand side. And then obviously finally it's at the target. But so there's a transformation right there, but we don't want to transform entirely to the target. We want to transform closer towards the target to retain smoothness. Again, that attributes itself to continuous time dynamics. So before I end, I'd like to thank the source of funding here. So this work was funded by the DCE, the Data Centric Engineering Program at the Engineering Institute, which is under the Roy Jurgensen Foundation, and also the UKRI. Also, I'd like to take this moment to advertise a seminar series that we host every 2 weeks at the Turing, and you can scan that for the link. And it's all about physics and machine learning. So we kind of gather speakers from around the world, and it's become a very popular platform. And even if you don't want to participate or present, but it could be a really good learning platform. So I encourage you to join. And with that, I say thank you. Thank you.